Okay, so having talked about jelly beans and ping pong balls, which are easy to understand and something we can measure, we're talking about the masses of elements. All the masses that are shown on the periodic table are determined the same way. This idea of relative masses. If you know the mass of one element, you can then find the masses of the other element. For instance, if you look at the periodic table, you will see carbon has a number 12.001 in its box. Okay, it has 6 protons, but the non-integer value in the box for carbon is 12.001. This can be atomic mass units, or AMU. All right, atomic mass units, AMU. That's for one atom of carbon. Hydrogen's relative atomic mass is 1.008 atomic mass units. Again, that's for one atom. Okay, and I said it again down here if you didn't get it. If we look at a molecule such as CH4 and we want to know how heavy it is, we need to see what it's made of, first of all. It's made of 1 carbon and 4 hydrogens. This subscript 4 means 4 H's. Okay, and then I'm going to look at the relative masses from the periodic table. So I have 1 carbon and the masses of 1, 2, 3, 4 hydrogens. If I add them up, I get 16.043 AMU. We could just call it 16, that'd be fine. And all we ever do for these is have the masses. So if I want the mass of water, H2O, it's made of 2 H's and 1 oxygen. So I'm gonna have the mass of 1 hydrogen, the mass of another hydrogen, the mass of oxygen, and that gives me 18.016 atomic mass units. So these are all relative masses. If you want to measure, where are we? So if we want to measure an equal number of carbon and oxygen atoms, where carbon weighs 12 atomic mass units and oxygen weighs 1, we have to look at the 16, where oxygen weighs 16, we have to look at the mass ratio, 12 to 16 or 3 to 4. 3 grams of carbon would have the same number of atoms as 4 grams of oxygen. All right, so with relative masses, if you've got that ratio of the masses, you'll have the same number of atoms. It turns out that when you're looking at the periodic table, I mean, we can't weigh AMU. They're way too small, but we can weigh grams. That's what our scales weigh in the lab, or our balances. We can directly convert AMUs on the periodic table to grams using Avogadro's number. Don't worry too much about this right now. 1 mole of atoms, 6.023 times 10 to the 23rd. When you have that many atoms, the atomic masses change to grams. That's it. So all we do, we look at the periodic table, say we look at chlorine. Chlorine weighs 35.45 atomic mass units. That's how much each atom weighs. If you're interested in a mole of atoms, or 6.02 times 10 to the 23rd of them, it is going to weigh 34.45 grams. So you can make this direct switch from the microscopic or submicroscopic world of the atom to the macroscopic world of the lab by just switching the units and using a large number of chlorines. So this is why chemists work in moles. Okay, the molar mass of any atom is given in grams. The formula mass, which is the mass of either an atom or molecule, is given in atomic mass units. So you need to know the difference between these guys, formula mass and molar mass. So we did CH4 before. Okay, 1 carbon, 4 hydrogens. We added up 12, plus 1, plus 1, plus 1, plus 1. It got 16. We had AMU, but now it's grams. So the molar mass of CH4 is 16 grams. The formula mass of CH4 is 16 atomic mass units. So you're going to look at those numbers on the periodic table and decide whether you're working with a lot of them, enough that you can see. We're going to then use them in grams, or you're using a tiny, tiny amount like atoms or molecules, and then their atomic mass units.